Hey everybody, and welcome to our 12th video lecture. We're going to talk about surface integrals, which we should think about as higher dimensional versions of the line integrals that we're already familiar with. So for line integrals, we thought about two basic kinds of integrals. The first kind were integral over c of a scalar valued function of x, y, and z ds, where ds here represents the differential arc length. So if f is taken to be just 1 constantly, this is going to give me the total length of the curve c. The other kind of line integral we thought about was line integrals of vector fields. This was the integral of c of f dot dr. And we're going to have analogs of each of these things for surfaces. In particular, we'll be able to integrate scalar functions over a surface, and since the surface is a two-dimensional object, it'll be some version of a double integral over my surface S of a scalar valued function of x, y, and z, and the differential element here is denoted ds. ds is the area of a local patch of the surface, differential area element. Alternatively, we can integrate a vector valued function over the surface, and this is given by the double integral over S of f dot ds with a vector symbol over the top. So S vector is a vector whose magnitude is ds, but it has a direction as well because it's a vector, and it's pointing out away from the surface. So this is something that's defined for what we're going to call oriented surfaces. So visually, what I should be thinking about there is a surface, for example, a ball like this, with some light glinting off it there, and what ds is it's the size of a little tiny patch. It's the area of a little tiny patch here. And ds vector is going to be exactly a vector with that magnitude pointing out away from the surface. So in particular, when I do this dot product here, I'll end up with a scalar at the end. And we want to come up with good interpretations of these surface integrals, as well as ways to calculate them explicitly. To start out, I want to talk about surface integrals of scalar functions. In other words, I want to talk about how to interpret the expression, the integral over a surface S of a function of 3 variables, ds. So if my surface here is something like this blue sphere, I should think about the integral doing is breaking up the surface into a bunch of nice patches, nice square patches which go around. And I'm just going to cover my surface with these patches, like so. And what I'm going to do is I'm going to sum over all the patches. This is going to be approximately the same thing as the sum over all the patches of the area of a particular patch times the value of the function at, say, the center of the patch. So this is a generalization of how we did integrals over areas in the plane, but now my areas, or my regions in the plane, don't have to be on a plane. They don't have to be flat. They can be like on a curved surface. And this is an approximation here. So as I take the limit, as I make my patches become finer and finer and finer, this is exactly the area. This is exactly the surface integral. And last lecture, we already figured out a way to get the area of a particular patch in the case that the surface is defined by a parametric equation. So let's suppose that S is defined by a parametric equation, x of uv, y of uv, and z of uv, where uv is restricted to be some points in some domain of interest in the UV plane. It could be some box in the UV plane, it could be the entire UV plane, it depends on the parameterization and the surface that we're interested in. In this case, the double integral of a function over S ds is going to be given by the integral over d of f of x uv, y uv, z uv. So this is now a function here of 2 variables, just u and v, because I've plugged in x, y, and z values for this with this particular parameterization. And I'm going to multiply this by the local area element, which is given by the magnitude of r sub u crossed with r sub v, those partial derivatives, du dv. So this is a nice, easy equation to remember. Though in practice it can be kind of hard to evaluate, because when I take the magnitude of that vector, I'll have some sort of square root type expression. And as we know, those can be tricky. More compactly, I can rewrite this equation as the double integral over s of f ds is going to be given by the double integral over d of f of r of uv times r sub u cross r sub v and magnitude du dv. And this is a nicer, more compact way of writing that. And here these double lines indicate that I'm taking the norm or the magnitude of that vector cross product. And we can also notice that in the special case when f is just the constant function 1, this is exactly giving me the equation that I derived before for the area of a parametric surface. So let's look at an example. In this example, I want to think about a sphere of radius a, and I want to calculate the double integral over s of x ds. To get this, I want to find a parameterization of my sphere, but last lecture we actually came up with one. It's just given by r of uv equals sine of v cosine of u, sine of v sine of u, and then cosine of v, all times a at the beginning. So this parameterizes a sphere of radius a. And we also calculated last time that the magnitude of Ru crossed Rv is given by a times sine of v. So my equation for the integral of the surface over the surface of x becomes a double integral here. And I should remember that in this parameterization, u is restricted to be between 0 and 2 pi, and v is restricted to be between 0 and pi. So this is the integral from 0 to pi, 0 to 2 pi, of x. So I need to plug in my particular x value, which is this value here. So it's going to be a times sine of v times cosine of u. And I'm going to multiply that by the magnitude of the cross product. So it'll be times a times sine of v du dv. And when I calculate this out, I'm going to have the integral from 0 to pi of a times sine of v squared times sine of u evaluated from 0 to 2 pi. I actually got an a squared, don't I? dv, but that's just the integral from 0 to pi of 0, which is just 0. In the special case that the surface that I'm looking at is given by the graph of a function for all x and y values in some domain D, there's a very obvious parameterization of the surface where I just take x to be u, y to be v, and z to be g of uv. And if I plug this into my equation before, this gives me that the double integral of my surface of any function of x, y, and z ds will just be equal to the double integral over the domain D. So for this parameterization here, uv will also have to be in D inside the uv plane of just f of u, v, and then for z I'm plugging in g of uv because that's what my parameterization says to do. And then I multiply this by r sub u crossed r sub v du dv. And let's check out what that is. So r sub u here is going to be the vector 1, 0, g sub u, and r sub v is going to be the vector 0, 1, g sub v. So their cross product, I can cheat to do this a little bit, and I can just put an I, a j, and a k up front, and take the determinant of the corresponding 3 by 3 matrix here, and I get the vector minus g sub u minus g sub v1. So the magnitude of ru crossed rv is going to be equal to the square root of g sub u squared plus g sub v squared plus 1. So my surface integral over S of f of xyz, the S in this particular case, is given by the double integral over d of f of uv g of uv times the square root of g sub u squared plus g sub v squared plus 1. And that's a pretty useful equation to remember. And in particular, I never really needed to do the change of variables from x to u and y to v. I could just let x and y be the parameters themselves. So to summarize, we have the following equation. If S is the surface given by z equals f of xy for some xy in the domain D, then the double integral over S of f of xyz ds is just given by the double integral over D of, oh, and I don't want to double use f here, so let's let the surface be given by g, and the function I'm integrating be given by f. So it'll be the integral of f of xy g of xy, which is a function of two variables only. So I'm just substituting in g in for z, multiplied by the square root of partial z partial x squared plus partial z partial y squared plus 1, all inside the radical dA. So this is a pretty useful equation, because a lot of the surfaces that we're interested in are actually given by graphs of functions, and many surfaces, at least locally, can be expressed this way. Let's look at an example. In this example, what I want to do is calculate the double integral over S of y ds, where here S is the surface given by z equals x plus y squared for x going between 0 and 1, and y going between 0 and 2. So in this case then, the double integral over S of y ds is given by the equation that we just mentioned. It's going to be the integral over that particular domain, so x goes from 0 to 1, and y goes from 0 to 2, of y times the square root of dz dx squared, so it's going to be 1 squared, plus dz dy squared, which is 2y squared, plus 1 dy dx. So this is the integral from 0 to 1, integral from 0 to 2, of y times the square root of 2 plus 4y squared dy dx. So this is the integral from 0 to 1 of 1/12 the quantity 2 plus 4y squared to the 3/2 power, which is equal to 1/12 times the quantity 18 to the 3/2 minus 2 to the 3/2. The next thing I want to talk about is how to do integrals of vector fields over surfaces. But in order to be able to do this, I need my surface to be oriented. So let's talk about that first. An orientation on a surface is a choice of direction that says which way is outward. So if I've got something like a paraboloid, on every particular point there, I can say, the outward direction is this way. And an orientation cannot suddenly switch outward direction. So at this point right here, I can't decide that it suddenly points inward. Outward needs to be the same as we go around. But at every particular point on the surface, we need a consistent outward direction. And that outward direction also needs to be a normal vector to the tangent plane to the surface locally. So there's only two choices. This is one possible orientation. The alternative orientation is where all of my local normal vectors point inward. And this is also a perfectly reasonable orientation of the surface. Albeit a little bit hard to draw. The first orientation is called a positive orientation. And the second orientation is a negative orientation. In the case that we close up these holes at the bottom here, so these are closed surfaces. It's interesting to note too that not every surface can even have an orientation. One of the famous examples of this is the Mobius strip. And you can make a Mobius strip right now. What you can do is just cut out a slim, long piece of paper, just like this, and then make exactly one turn in it. Just twist it one time, and then just tape it back together. And now if I try to put an orientation on this thing, then locally here I need to decide which direction my normal vector is going to point. It could point that way or the other direction. Let's just choose this one. I'm walking along here, I need to be consistent, so these need to all point out that way. When I get behind here, they're pointing out this way, away from the thing, in a way that you can't see. So let me do dots. This one here, dots and points out. This one here, dots and points out. And so on. I'm just going around like this. And when I get to here, it's pointing outwards. When I get to here, it's pointing outwards. And then I'm going around this thing, so when I get over here, since the paper curved, I'm going to pointing dots and pointing out this way. And now when I'm back here, dots and pointing out this way. And in particular, when I get back to this point, it should be pointing out the way it was before, but now it's pointing inward. So somehow something's gone terribly, terribly wrong. This is a really interesting surface in the sense that on this surface, if I'm looking at it, this looks like it's the outside of the surface. And this looks like it's the inside of the surface. But I can start on the outside, and I can travel on the outside. So I'm getting a dotted line because I'm on the outside there. And then I pop back over here. And I'm on the outside still, just like before. But by the time I reach back over here, I end up on the inside. So I started out on the outside, and then I end up on the inside as I go around. I go on the inside now. And I'm on the inside. And then I pop back out on the outside once more. So this is a really interesting thing. And if you construct this at home, you can double check that once I've made my Mobius strip, I can draw a line along the Mobius strip without ever taking that pen off the paper in such a way that the line that I draw goes on the outside and what I think is the inside too. And this is just saying that for this particular surface, there is no outside, there is no inside. It's not a two-sided thing. The surface only has a single side. And that's pretty interesting to think about, that there can be one-sided surfaces. In fact, I can even find one-sided closed surfaces. An example of this would be the Klein bottle. But this is a little bit hard to draw a picture of, though you can look up some pictures online. And in particular, to really get the Klein bottle, you need to have it sit inside a 4-dimensional space, R4, rather than just a 3-dimensional space. We say that a surface is orientable if we can put an orientation on it, and for closed surfaces, we can even decide which orientation is which. In particular, closed surfaces have an outside and an inside. The inside being where there's a finite amount of space, and the outside being where there's an infinite amount of space. So, the one where the normal vectors point outwards is the positive orientation, and when the normal vectors point inwards, it's the negative orientation. So let's think about surface integrals of vector fields. So I want to try to interpret the expression, the integral over S of f dot ds. ds here is a vector which points in the direction of the normal vector to the surface. And as we were talking about before, there's two different possible ways that could point. That could point, for a closed surface, outwards or inwards. So this is something that's defined for oriented surfaces. So here I want S to be an oriented surface. Which is a surface with a chosen orientation. So then ds here is a local vector which points in the direction of that orientation. And the way that this vector integral then is defined is it's defined to be the integral over the surface of the dot product of f with the local normal unit vector. That's a unit vector which is normal to the surface locally and which points in the direction of the chosen orientation. So this is now a scalar, and I'm going to integrate that with respect to the local area element ds. So now this is just a surface integral of a scalar valued function like we've already talked about. And these sort of integrals are oftentimes called flux integrals. And the intuition behind that, let's think about a box which is submerged in water. And the water is moving around, so locally, the movement of the water is described by a vector, which is the local velocity. So water can in particular move in and out of this opening in the top of my box. And if I want to figure out, maybe I want to figure out how much water is moving in and out of the top. So what I can do to do that is I can do the integral over this blue surface S I've drawn in the top. And this isn't a real part of my box. My box is open here, but I'm imagining this blue surface, this imaginary surface S. And the double integral over S of f dot ds is exactly giving me the flux of the water through that surface. So this is the total amount of water of the volume of water in my box. In particular, if I were to multiply that by the density, this would be the total rate of change of the mass in that case of the water in my box. Well, let's examine this flux integral further, or this integral over a surface of our vector field. One thing that we can do is we can simplify the equation for it quite a bit. So I can write this down now. This is the integral of f dot the local normal unit vector ds. And now if s is parametrized by some function r of uv, I know that a normal vector to the surface at any particular value uv is just given by r sub u crossed r sub v. And one pointing in exactly the opposite direction is minus r sub u crossed r sub v. So a choice of orientation of my surface locally is just choosing which one of these two expressions I want. And let's say that my orientation is this guy here. Then once I have that, I can express my surface integral This is going to be the double integral over S of f dot the normal local unit vector. So this is a normal vector, but it's not a unit vector. To make it a unit vector, I'm going to divide it by its magnitude. So divide it by RU crossed RV, and then I'm going to multiply it by ds. And if I remember before, ds is the same thing as the magnitude of RU crossed RV. That's the local area element times du dv. That's what ds is. And these two guys cancel off. So I can rewrite my area integral as the double integral over d when I'm integrating in u and v now of f of uv dotted with ru cross rv du dv. And if I wanted to choose the other orientation, that's just going to put a minus sign here. So there's this, the area integral is plus or minus depending on the orientation. So this is the equation that we want to remember when we're calculating these things. One of the things that's really nice about this equation too is that there's no magnitude of RU cross RV. So that means right away we're going to get rid of that square root expression that we could have in some other situations. And we can compare this expression to the expression that we got for line integrals, where the line integral of a vector field was just given by the integral of f of r of t dotted with r prime of t dt. It's very, very similar sort of expression. And I should be more explicit here when I say f of uv. What I really mean by this is f of r of uv. Because f is a function which takes in x, y, and z. And r is a function which takes in u of v and gives us an x, y, and z. So let me not be sloppy about that notation and write this very explicitly. Let's do an example. In this example, I want to evaluate the double integral over S of f dot ds, where f is this vector field yxz, and S is the boundary of the solid region enclosed by the paraboloid z equals 1 minus x squared minus y squared, and z equals 0. So S is the surface whose top is this paraboloid, and whose bottom is this flat part of this plane here. And whenever the orientation of a closed surface isn't specified, we should assume what we mean here is just the traditional outward orientation. So this is our orientation that I'm drawing in here. And on the bottom, these things always just point directly downward. They're normal to the surface, and they're always pointing away from the interior. Now to do this integral, the surface integral, I need to break it up into two separate integrals. One for the top part, and one for the bottom. And that's because we've got to break it up over any sort of kinks or anything we find. So the double integral over S of f dot ds is going to be equal to the double integral over, let's call it S1 of f dot ds, plus the double integral over S2 of f dot ds, where here we'll let S1 be the top part and S2 be the bottom part. So let's try to calculate these double integrals now. The upper surface has the parameterization r of xy is equal to x, y, 1 minus x squared minus y squared, just because it's given by a function. So r sub x is given by 1, 0 minus 2x, and r sub y is given by 0, 1 minus 2y, and their cross product, rx cross ry, is given by 2x, 2y, and 1. So what I need to decide first and foremost is if I should use rx cross ry, or should I use negative rx cross ry. And that has to do with the orientation that I'm choosing. But if I'm looking here at this particular vector, in order for these to point outwards, in particular for it to point outwards at the very top like it should, the z component there should be positive. So I want Rx cross Ry. I don't want minus Rx cross Ry. It already has the correct orientation to be outward. So that means the double integral over S1 of f dot ds vector is going to be equal to the integral of my vector field, f, which was, again, y, x, z in this particular problem, dotted with my Rx cross Ry vector, 2x, 2y, 1, dA, and I'm going to integrate it over the domain that I'm considering. And I want to look back at my parameterization. What domain should I integrate this over? And it's very clear to me right now. It should be integrated over the circle. So this is integrated over the circle, x squared plus y squared less than or equal to 1. So let me write down this double integral as minus, it's the double integral over that disk of minus 2xy, sorry, 2xy times 2xy plus z dA. And to do that double integral, it makes sense to switch to polar coordinates. So this is the integral from 0 to 2 pi, and the integral from 0 to 1 of, remember my polar coordinates here, x is r cosine theta, y is r sine theta. So this is 2r squared cosine theta sine theta. That's what this first expression becomes. But I've got two of those, so I might as well just make that a 4. And then also, I need to worry about the z expression. What in the heck is z here? Well, if I remember my parameterization, z was this third term here, so z is 1 minus x squared minus y squared. So this I should replace just by 1 minus x squared minus y squared, which in polar coordinates is going to be the same thing as 1 minus r squared. So this is plus 1 minus r squared. And then to do integration in polar coordinates, I need to multiply everything by r, dr d theta. And I assume that we can all evaluate this, no problem. This gives us pi over 2. Now the integral over S2 of f dot ds is a little bit different. And to parameterize that surface, I could think about just writing down a parametric equation for a plane. But I don't really actually need to go that far because the local normal unit vector is just going to be 0, 0, minus 1. So it's actually easier if I just write down that this is the integral over S2 of f dot the local normal unit vector ds. So this is going from s vector into s scalar now. There's no vector symbol over my s anymore. And this is just the integral over S2 of my f vector field, which was y, x, z. I'm dotting that with the local normal unit vector, which is going to be pointing in the z direction but pointing straight downwards, so 0, 0, minus 1 ds. So this is just the integral over that closed disk in the xy plane of minus z ds. And I'm remembering here that z is going to be 1 minus r squared. So this is the integral from 0 to 2 pi, integral from 0 to 1 of minus 1 minus r squared times r dr d theta. And this is, when I calculated everything out, minus pi over 2. Oh, hold on a second. I've completely messed this up, haven't I? So on that bottom surface, I'm in the xy plane. So on the bottom surface, z is not equal to 1 minus x squared minus y squared. On the bottom surface, z is equal to 0. So what I'm actually doing here is a very easy integral. It's just the integral over 0 of 0 over that bottom surface. So all told here, I just get 0. So my total surface integral then is just obtained by adding those two things together. And it's just going to be pi over 2 plus 0, which of course is just pi over 2. So surface integrals are a pretty awesome tool, but as we've seen, they can be a little tricky to calculate, and it's really important that you get some practice with this. Extra practice is also very good, so going beyond the homework problems into additional problems in your textbook is not a bad idea at all. But this is a pretty good stopping point, and next time we'll pick things up again with Stokes' theorem, which is a really great theorem that can relate integrals over surfaces of vector fields to line integrals on the boundaries of those surfaces. So it's really good stuff, and I'll see you guys there.